Everyone. I kindly welcome you all to the webinar on impact of measures taken during COVID-19 on pollution, organized by Department of Applied Sciences, Parul University. Today we have the presence of Dr. Ekta Shah, Assistant Professor in Nirma University. Warmly welcome you, ma'am. Dr. Ekta Shah has recently received her PhD degree from Gujarat University. She has received gold medal in Bachelor of Science at Maharaja Sayajirao University, Baroda. In 2017, she qualified Gujarat State Eligibility Test, that is GSET, for assistant professor. Also, she received fellowship for PhD funded by UGC granted National Fellowship. She served as a lecturer at Parul Polytechnic Institute, Parul University in 2015. In 2017, she was a visiting faculty for Remedial Mathematics and Applied Mathematics at Sumandal Vidyapith. Her areas of interest are modeling in dynamic system and control theory. She has also keen knowledge regarding software such as MATLAB, Maple, and so on. She has more than 10 research papers published in national and international Scopus Index as well as Web of Science journals. She has also published papers in books such as SCIR application for crop through water and soil texture, advances in applied mathematical analysis and applications, review publishing, Web of Science Scopus, fractional order model to visualize the effect of plastic pollution on brain, mathematical models of infectious diseases and social issues, IGI Global, international academic publisher. Bio-waste management during COVID-19, mathematical analysis of COVID-19 transmission, Springer book. Global stability analysis through graph theory for smartphone usage during COVID-19 pandemic, mathematical analysis for COVID-19 transmission, Springer, and many more. Also, she has presented research papers and secured prizes in international as well as national conferences. I kindly invite Dr. Ekta Shah as a speaker for today's webinar. Please, ma'am, you may begin.
Thank you for such a kind introduction. Is my screen visible?
Yes, it's
Is my
visible.
okay, ma'am. So, as I've already introduced, I let start the impact of measures taken during COVID-19 on pollutions. Here, I will discuss two models, that is, pollution due to lockdown and pollution due to bio-waste. So, first model, that is the positive impact of lockdown due to COVID-19 on pollution. For that, let us discuss some COVID-19 period. As we know, the outbreak of novel coronavirus disease, namely COVID-19, has become an international public health issue in very short time period. To control this dispersal of this disease from its sources, more than a third part of world population have blocked transnational transportation, forbidden industrial unit, and restrict the non-essential movement in the country, which substantially mitigated the transmission of COVID-19. The COVID-19 was first identified in Wuhan city of China in late December 2019. Following some subsequent months, the disease spread quickly to the rest of the world and declared as a pandemic outbreak by WHO. Several control strategies are worked to control the transmission of the disease. Besides to follow social distancing, the lockdown has been proven to be an effective control measure in many countries. The COVID-19 is a respiratory infection caused by a coronavirus, that is COVID-19. The virus could stay sustainable in aerosols for some hours. Therefore, It is interesting to explore the effect of lockdown caused by the COVID-19 outbreak on air pollution. Quantitative analysis of the conversion rate of air pollution due to this current lockdown situation may provide a useful information to develop an effective strategies to make pollution-free society. Jarvis and his research team have found that lockdown strategy results in 74% reduction in the average daily number of contacts, which would be able to reduce the value of basic reproduction number from 2.6 to 0.62. I will discuss later on this basic reproduction number. Almost all infected countries have been blocked, right? And we know that human healthiness is intentionally influenced by the quality of air. In addition, preceding studies have been recommended that exposure to air pollutants for a long time period influences several respiratory infections. As stated by the State of Global Air Report, approximately 5 million people died globally in the year 2017 due to this air pollution. But as a positive outcome of this unexpected lockdown condition, that is a major reduction is found in the air pollution in many countries. So I used the mathematical model on it. Let's understand what is the mathematical model. It plays a crucial role to analyze the available data and generate a strongly applicable output. Acuna and Jagara et al. Model and proves that an optimum value of the lockdown period, which curtails incidence and consequently this incidence peak date falls later than the government evaluations. So in my present work, a mathematical model has been created by considering two compartments, that is lockdown and the pollution. As the coronavirus pandemic remains to take hold of in the world, the government decided and imposed lockdown to curb the disease spread. More than a third part of world population is under restriction and obeying lockdown rules due to this COVID-19 pandemic. People stay indoors resulted less traffic and a reduction in industrial activities, and hence Earth's condition is improving as pollution decreases than the usual. So let us discuss this mathematical modeling. What is it? A mathematical model is the formulation of real world situation using the mathematical language, and it interprets the using these mathematical tools like MATLAB, Maple, right, and phenomenon, which describes a distinctive human idea of replication nature. A mathematical model depicts the behavior of the problem, and it gives us accurate results which help to increase the immunity of the society. Here is the flow of mathematical modeling, that first we consider one environmental problem, then we have derived the mathematical model by considering some assumptions. We are formulating the governing equations. By solving this equation, we have some analytic asymptotic numerical results, and then we simulate the model. By interpretation of this simulating model, we receive some results and end with it. So we have some information by and we also predict the results. This is the mathematical modeling. Continue. The process of developing, describing, analyzing, and then validating a model is called a mathematical modeling. It is based on three rationales, that is, reflecting the behavior of the problem, explain the necessity of the behavior that exists, and allowing the focusing. The process requires the proper combination of variable and parameters. Using this combination, the system of nonlinear ordinary differential equation is derived, which togetherly forms a model system. Now there are different type of mathematical model, that is dynamical model, statistical model, game theoretical model, and computer model. But I here will discuss dynamical model. So first we understand what is the dynamical system. The mathematical model of interest is the dynamical model referred as a dynamical system. A dynamical system is a system of nonlinear ordinary differential equation which is dependent on the time t. For the continuous real time, the system can be formulated using nonlinear ordinary differential equation, that are the ODE. And the agenda of this system is to study the qualitative behavior of the system solutions. We can formulate the system of nonlinear differential equation by given this equation number 1, where x bar of t belongs to Rn is a model compartment and time derivative. Equation 1 is a dynamical system with a finite dimensional state, that is x bar of R n tuple. Then we understand compartmental model, because I will use here only compartmental model. In this dynamical model, the problem is divided into compartments with the characteristics that variables in each compartment have homogeneous characteristics. Therefore, these models are also known as compartmental model. In model, we are dividing this x bar into x1, x2, xn. These are the compartmental, and then it will be some function of t. So, using the definition of this f of x bar, the system can be replaced by taking the derivative of each compartment. And this will reflect the rate of change in each compartment with respect to time. So by considering this whole scenario, I have developed the model by considering two compartments, that is lockdown and the pollution. Here, this LDN stands for lockdown. B1 is the growth rate of lockdown, means the period which it will consider. C is the catchability constant. M stands for lockdown decreasing rate due to well medication facility. Gamma is the impact rate of pollution due to vehicle emission in this emerging lockdown period. Epsilon is the proportionality constant. K is the carrying capacity of lockdown. It has very wide role. And the mu1 is the depletion rate of lockdown. Then we have rate of change in pollution, in which P stands for amount of pollution. B2 is the growth rate of pollution, and mu2 is the depletion rate of pollution. Here, as I said, that carrying capacity of lockdown play a very wide role. It shows the capacity of an area or any region in which the whole population can be quarantined without breaking a social distancing. It also depends on the population density of the region. Higher the population density, lower the carrying capacity. So solving this system of two equations, we have solution which called equilibrium points. Let me understand first equilibrium points. An equilibrium point of a dynamical system is at a fixed point, which means solution that does not change with time. An equilibrium point occurs when each equation of dynamical system is set to be zero, that is, Fi of x equals to 0. And equilibrium point are constant functions which satisfy the dynamical system. So for this system, we have two equilibrium points. First one is lockdown free equilibrium point and second one is endemic, that is the optimum issue point. Next term is basic reproduction number, that is R0. It represents the expected newly infected individuals from the infected individuals in a susceptible population. This helps to predict whether the disease will spread in a society or die out. Dagman et al. Has described the method of finding threshold using the simplification of the Jacobian matrix. So this rate is affected by several factors including the time duration of effect, the effectiveness of the issues, and the number of susceptible people with whom the affected people comes in contact. Significance of this R0, that is R0 of a dynamical system, is computed by using the next generation matrix method. If it is less than 1, then the model will be stable, and if it is greater than 1, then the model will be unstable. So threshold quantity is considered as the prevalence of the output, and hence the dynamics of the model is determined by R0 so far. So for this system, we have this is the next generation matrix method. We are evaluating the Jacobian matrix of the system, that is f of xi at equilibrium point E0, and V f considers the non-linear part of the equation and V includes the other part. And then we calculate this Fv inverse, which represent the basic reduction number. So for this model, we have derived this F and V in terms of this given by mathematical expression. By calculating all the parametric values from the given references, we have observed that R0 equals to 0.7125. It indicates that 71.25% pollution is reduced due to this lockdown period. Next, we have bifurcation theory. Bifurcation helps us to framework the qualitative change of the system. A bifurcation occurs when a small and smooth variation is made to the value of model parameter, which leads to a rapid qualitative change in its nature. We can see the significant impact on the solution while using the bifurcation analysis. Terminology which is used in this bifurcation, that is the parameter which set to be varied, is known as the bifurcation parameter, and the curve which reflects the qualitative nature of the system or a particular point is called a bifurcation curve. Here we have focused on the backward bifurcation. So for this system, that is lockdown and pollution, we have gained this graph, and this simulation specifies the unstable to stable condition, which means that the model approaches a stable behavior. So if lockdown tends to stable, it changes the pollution and improves the air quality. It may decrease, which is analyzed in a further section of simulation. So we have applied the optimal control theory. Here we are basically, the optimal control is used to control the situation and optimize the solution. It has made a significant role in a dynamical system, and it deals with finding a control over a period of time such that objective function is optimized. This theory includes state equations, a set of constraints, and control variables. Optimizing an issue is a fundamental tool in the world of this dynamical modeling. It can improve the results. And optimization of dynamical modeling is done through control theory. Coincidentally, this lockdown is beneficial not only for controlling the spreading of disease but also decontaminates the environment. So, the purpose of this theory is to decrease the pollution by extend the lockdown period without losing the economic condition which is taken as the control U1. So I have applied the control U1. I am increasing the lockdown period which decreases the pollution. Let us see the effect. First, the objective function of this corresponding phenomena is given by this mathematical expression, that is J of Ci and omega, lambda region. Lambda is the feasible region for the this corresponding model. Then we have Lagrangian function for the corresponding objective function. And after all the computation, it gives the resulting condition for the optimal control as a U1 star. Now, let's see the numerical simulation part. This is the trajectory curve towards lockdown towards the pollution. So, this directed graph shows that imposing the lockdown decreases the concentration of pollutants such as traffic, industrial activities, social gathering, everything has been reduced. Increasing in lockdown period results in a reduction in pollution, which can be analyzed through this direction of arrows. You can see here over. Now the consequences on the pollution by varying the value of K, that is the carrying capacity, and the gamma, that is the impact rate of pollution due to vehicle emission. We can see that as we are increases the carrying capacity by 10%, pollution decreases by 0.8%, and pollution due to vehicle emission increases, pollution decreases by 6.5%. These results are because of lockdown period, otherwise this percentage will be high. And this drop off due to lockdown is very appreciable. It should be remarkable period in all over the world. Now we have done also sensitivity analysis where B1, that is the growth rate of lockdown, and mu1, that is the depletion rate of lockdown, has positive impact on the model. Then we have also record that the constant C, that is the catchability constant, and capital M, that is the lockdown decreasing rate due to well medication facility, have a negative effect on the lockdown. And you can see that other parameters have a very negligible effect, as threshold value, that is the R0, depends on the B1 and mu1. Then we have effect of lockdown strategy, effect of control strategy on the model. As we have applied the control on the model, it suggests that 18.05% increase in lockdown results into the reduction of pollution up to 26.74%, which is a very valuable outcome for the environment. But now, lockdown for a lifetime is not possible. So I suggest that lockdown for a week, once in a week or once in a month, it is very highly appreciable. Now let us discuss the model 2, that is the bio-waste management during this COVID-19 period. So COVID-19 is such a contagious and contaminant disease in which plastic plays a vital role in making confident social worker to deal with it. As per the latest 2020 WHO evaluation, The world has consumed 89 million masks, 30 million gowns, 1.59 million goggles, and 76 million gloves per month alone due to COVID 19. As these things cannot be reused, it can only be dumped or recycled, becomes the waste. Thus, along with this PPE kit and sanitization, this biomedical waste is also big challenge for any hospital having COVID-19 patients. These all data are taken from 2020, right? Here it will also increase. So much bio waste will be produced. The waste produced by healthcare taken at home during COVID-19 pandemic time is also classified as bio-waste. But in this research, I have included only bio-waste produced due to hospitalization. This data has been taken on July 23, 2020. And in March 2020, the government of India has released guidelines for handling the safe disposal of bio-waste generated during the treatment of patient having the novel coronavirus. If from this guideline, if the people follow this guideline, then transmission of COVID-19 and also this pollution produced by this bio waste can also be controlled. As I have seen that biomedical waste is divided into three parts, that is 75 to 85% bio waste is created by non-infectious disease, and then 10 to 15% biomedical waste is infectious also, and 5 to 10% are produced by hazardous. So I try to develop the model by considering this scenario having four compartments. First is COVID infected individuals who are getting hospitalized, which create the density of biowaste and emerges the pollution. These all are rates which are connecting each and every compartment. All the parametric values are taken from Worldometer on July 23, 2020. Here we have formulated the system of differential equation. Here I have used the concept that rates which are entering into the compartment are to be added to the differential equation, and the rates which are going away from the compartment are to be subtracted from the differential equation. So from this system of equation, by solving it we have two equilibrium point, that is pollution free equilibrium point and optimum issue point. In pollution free, you can see that there is absence of this pollution compartment, and optimum issue point means it has optimum values at each compartment. For this model, also we have calculated the basic reproduction number, also called the good value. For this, we use same scenario, that is the next generation matrix method. This is the F part of this model, and this is the V part, that is of this model, bio-waste model. And by evaluating the mathematical expression and substituting all the parametric values, we observe that 23.64% pollution is produced by only this bio-waste. Now the local stability of this model. Theorem 1, that is, here we have stability analyzed at each equilibrium point. And here we have two equilibrium points. So first, that is pollution free equilibrium point E0 is locally asymptotically stable if this condition hold, that is B beta is less than mu1 into gamma 1 plus mu2, and E star is locally asymptotically stable if this condition, this given mathematical expression holds. So one can advise that if beta, that is the rate at which infected people getting hospitalized, is lesser, then the model will be stable. Global stability. Here I have analyzed this local stability through Ruth Harvey's criteria. And this global stability is analyzed through using by Lipno function. This it is also analyzed through at each equilibrium point, that is E0 and E star. First theorem says that the pollution-free equilibrium point E0 is globally asymptotically stable if R0, that is our threshold value, also called a basic production number, is less than or equal to 1. Theorem 4, that is at global stability analyzed at E star, which means at optimum issue point, it is globally asymptotically stable if this ratio of each compartment with its optimum value is less than 1. Now the optimal control theory, these all four compartments we have applied the control. First control U1, that is COVID-19 infected people. Okay, so here we have applied the control on the COVID-19 infected people to decrease the hospitalization. So if will decrease, then it will results into the other. Then U2 control is applied on the hospitalization people, which decreases the bio waste. And third control is applied on the amount of bio waste material that can optimize the pollution. So basically, we are optimizing the pollution. So for this system, the corresponding objective function and Lagrangian function is given by capital J and capital L respectively, and by computing all the calculation and applying the control theory, we have optimum value of each control is described by this U1 star, U2 star and the U3 star. There is much calculation behind of it. We are taking partial derivatives with respect to U1, U2, U3 of this Lagrangian function, and also evaluating the all compartmental partial derivative. And then we are moving on the numerical simulation part of this model. This graph, that is COVID infected individuals, this is graph of hospitalized individuals, bio waste, and which creates the pollution. So one can observe that COVID infected individuals are getting hospitalized, and this interprets that after approximately 1 week, bio waste is generated during the pandemic. This collection of bio waste creates the pollution after 3.5 weeks if there is not taken any solution to prevent this thing from this bio waste. This directed graph, this is the QR. This all results are simulated by using the MATLAB software. Here This directed off graph shows that as hospitalization means people who are getting hospitalized through this COVID-19 scenario, if it is increases, the pollution increases, and hence medical staff has to use the safety things for the protection. So it increases the bio waste, and this bio waste creates to produce and increasing the pollution at each month. So from this direction of arrows, we can see that as pollution increases, as hospitalization increases in x-axis, this pollution is also going to be increase and increase. Similarly, this as bio waste this increase pollution that is on noted on y-axis, it also increases, and you can see also the intensity of the arrows. Means as intensity increases, the amount of pollution also increases. Now we have another simulation that is based on the number r0 which is our threshold value, very effective very effective number for the model, right? So b, that is the growth rate, and the beta, that is the hospitalization rate, as it increases, you can see that r0 also increases linearly. So we can say that these parameters b and beta are very sensitive to the threshold value and hence the model. Therefore, if both the parameters, that is b and beta, that is the growth rate and the hospitalization rate, if it is undertaken care, which means that if the infected people are getting cured by only home isolation, means we are not taking him or taking them at in hospital, so hospitalization obviously decreases, right? So it will reduce the pollution also. So one can say that if we are taken care of this b and beta, pollution maybe is in control. Now then we have applied the optimal control on this model. So here we have three optimal control. First is optimal control as a treatment on COVID-19 infected people to optimize the hospitalization. Control U2 is a treatment on hospitalized individuals to increase the bias. And third control is on this bio-waste. It is a treatment, optimal control as a treatment on a bio-waste material to reduce the pollution. So all three optimal controls are applied to the system as a treatment. Basically, again we are reducing the pollution due to which is the produced by this biomedical waste. So after applying this optimal control theory to the model, we have observed that